Thanks everyone for calling in. I'm going to give an update on the Scream project. And so this is a project that I'm leading, but I would say I'm loosely holding the reins, and the group of people that I've listed have been doing a fantastic job of kind of pushing everything forward. So, and I should also mention that a lot of the people that I'm listing here are not actually officially on the Scream project, but they're on related projects, and it's made sense to collaborate. So to start out with some background and context, these are slides that you've probably all seen before, so I'm going to go through them relatively quick, but I think that setting the stage is important. So first, the S in Scream is for simple, because I believe that you shouldn't trust results you don't understand physically. So if you have a more complex parameterization, it may give you better answers, but actually can stand in the way of having trust in your predictions. Simplicity was also really critical because we are trying to do a complete rewrite of the model in C++ in order to get the new performance that we need. And we can't do that if we have a huge code base. And this rewrite is critical because it allows us to run at very high resolution, which means that a lot of things that were subgrid scale and needed to be parameterized hopefully will be explicitly resolved. So it makes sense to have a simpler model. And so there's kind of a virtuous cycle here between simplicity allowing us to rewrite in an efficient way, which allows us to run at higher resolution where we don't need as complex parameterizations. So, our target resolution is going to be 3 kilometers globally. With 128 vertical layers, we're decreasing the model top back down to 40 kilometers like E3SMV0 because we're really trying to target the lower troposphere with as high resolution as we can. And I am personally very excited about opportunities for coupled modeling in this framework. And so I think it's important that this is an atmosphere model, but we should already have ocean and sea ice models that work at these scales. And so we should do coupled modeling, hopefully relatively soon. So why does it make sense to go to such high resolution in the atmosphere? And I think the reason is that a lot of the really important climate processes, in particular related to clouds, occur on kilometer scale. And so I have this kind of cartoon showing things. There's a distance scale in kind of the middle bottom of the picture there for 10 kilometers. So you can see a lot of these things are around a 3 kilometer scale. And so we've known for a long time that parameterizing subgrid processes is a really hard thing to do, right? People's been working at it for 50 years. And I would argue that if you have a parameterization it's really hard to figure out, that causes a lot of uncertainty in the predictions you make with it. And so explicitly resolving things, I think, is really critical for improving our predictive credibility. And so you don't get anything for free. We're going to much higher horizontal resolution and vertical resolution. And what we have to pay for that is that we don't get to do the centennial length climate simulations that we're used to doing. And the main reason for this is even if we had a computer where we could run each column of the model on its own core, we still wouldn't be able to simulations that are so long, because as your resolution increases, CFL stability requires you to use shorter and shorter time steps. And so if we can afford to run 1 billion time steps, that's going to get us much less simulated years if we have to use a time step that's, say, 10 times smaller. But I think that that's okay. One of the main theses of this whole project is the idea that climate change can be understood from short runs. So that's not something that we're exploring so much now because we're just trying to build a model, but it will be in the next phase a really critical component. I'm bullish on our ability to do this because we know that clouds, we've known for a really long time that clouds are the main source of climate uncertainty, and we also know that clouds respond very rapidly to forcing changes. And so if we have cleverly designed short runs, I think that we can really tease out what climate change is going to happen in the future. And so coming up with new clever ways of doing this, I think is a critical job for us in the next round of E3SM. But some really useful short tests already exist. And so one of them are these SES simulations where you prescribe a uniform or prescribe an SST increase and read off what the resulting change in top of atmosphere radiation is. From that, you can get the feedback parameter or the cloud feedback parameters I'm showing on this plot on the right-hand side. So on the x-axis, we have model predictions of the cloud feedback from these SES experiments. On the y-axis, we have the corresponding values from the same models using the coupled, more expensive 4 times CO2 type of experiments. You can see that for the most part, you get basically identical answers both ways, and it's so much cheaper to do the SES type experiment. So in terms of the processes that are going to be included in the SCREAM model, the first thing is that we're not parameterizing at least deep convection. That's something that should be pretty well resolved at 3 kilometer resolution. We are going to continue to parameterize shallow convection as part of our turbulence and cloud scheme, which is called SHOCK. And you can think of SHOCK as a simplified version of the club parameterization that we're currently using in E3SM v1. So it's a bit of a simplification / evolution. Similarly, we're going to continue to use the spectral element approach that we're using in E3SM v1 for the fluid dynamics. This is going to be a non-hydrostatic version, of course, rewritten in C++ as well. Radiation is going to be, I guess, also an evolution. It's the RTMG-P package, the successor to RTMG, which is GPU ready and has a lot of science advancements as well. Relatively different microphysics scheme. We're going to use P3, which is very, very popular in the weather forecasting community. And so aerosols we're going to prescribe in the initial implementation is a whole separate project called EAGLES to implement a new prognostic aerosol scheme. Although I will point out that I'll talk later about how we're going to have a Fortran and a C++ initial implementation. The Fortran implementation that we have is going to be able to run MAM4, so we should be able to do aerosol research probably in the next year or so. It's important to keep in mind that we're not the only modeling center that is targeting these very high resolutions. And in fact, there was an intercomparison last year involving 9 models, which are listed on the right-hand side, where they all did 40-day simulations with less than 5 kilometer global resolution. And so we're playing catch up in a sense, but I think that there are some unique aspects to our project that's going to make E3SM a leader in this field. One of those is the shock parameterization I talked about before. It's more sophisticated than other modeling centers are using. One of the things that it does is it allows us to capture subgrid shallow convection, which I think is a really critical lack in the other models. Another related concern is shown in this graphic, where we have on the top an all or nothing kind of cloud scheme where you either have 100% cloud fraction if you're saturated or 0 if you don't. And what we're showing, this is a different models, a regional cloud resolving model simulation of shallow convection. And the black is the LES, so that's the kind of synthetic observations we're targeting to. The different colors are different horizontal resolutions. And you can see that we're not converging very well in horizontal resolution at all, or at least we have a lot of sensitivity. And when we switch to using shock, we have a lot less. And so this is an illustration of the point 2 that I think is an E3SM novelty, is that in the SCREAM team, we're really obsessed with testing. Our goal is to make sure that we have a model that's convergent in X, Z, and T, and that basically we want to make sure that we don't have any errors. And so we're working very hard at that. I'll talk more about that later. As I mentioned before, SCREAM is going to be written in C++ with the COCOS library, which allows us to run on GPUs. And that is, I think, a critical advantage because that allows us to use the newest, fastest architectures and will allow us to run on DOE's exascale machines. We also have one of the fastest Dicors out there, and we're going to have this simple, streamlined physics code. So we should have a really fast model, and I believe that we'll be able to do longer and higher resolution simulations than other centers can manage. So, and then again, we already have an ocean ice capable of running at very high resolution to work with. So I think that will be great as well. So in terms of the plan of how we intend to put all of this stuff together, there's 3 stages to the project, and I'm trying to illustrate them in this kind of 2-dimensional graphic where on the x-axis we have time into the project, so it's supposed to end July 2021, and the vertical is giving the fraction of team members that are working on any particular task. And so the first stage you can see is all of these different little colored boxes where we're basically putting the model together, and that is more or less, well, it's done now, and that has produced what we're calling Scream V0, which is a Fortran version of the Scream model, which is basically running it's running in the E3SM framework. So, and we're able to run it in E1024. I'll talk more about that later. So in addition to the V0 version, we have our real goal, which is Scream V1, which is taking all these parameterizations, using the Fortran as a template, porting them to C++ Cocos, and this is where we're really kind of staking our claim on tests, so a lot of unit tests. And then a related bit of that is the coupler effort as well. So now moving on to talk about the Fortran version of the model. I told you that it runs. I'm showing here just a cool snapshot of results we have after 2.5 simulated days. So precipitations and color, the liquid water path is kind of the fake cloudiness you see. And so you see the storm tracks, you see cumulus off the coast of North America. And so this looks like Earth mostly, I'll say. I think in the next slide or two, I'll show some issues that we're working on, but really we're pretty happy with it. To put a positive spin on our performance, we run in real time, which we could say a little bit more negatively is we're getting something like 1 simulated day per wall day, which is not what you hope to see in a climate simulation. But I should say that we're using the fewest number of nodes that we can actually run any 1024 on, and we haven't done any performance tuning at all, and the Fortran version was never meant to be performant. So it's this is just a kind of a number to keep in mind rather than something that we should feel bad about. Something I'm particularly excited is we recently switched to using the Scorpio PIO2 for doing our output. This is really critical because previously we were spending almost all of our time writing our restart files rather than actually doing any time stepping. And so this is great. We think we're going to be even faster when we get to use the adios option in Scorpio, which isn't quite ready yet, but hopefully will be in the next week or two. And adios just allows you, instead of having one file being written per time step, you have each of the nodes is writing output writes its own file. And this is really critical because we spend most of our time in output not actually writing the files, but communicating the information to the locations to write the files. So that should be better. And then, so in terms of the near-term plan, we are really hoping to participate in the next round of Diamond. I think that's important because we want to establish ourselves as one of the world's leading groups in doing this. And so having some publicity is important in that regard. And also, I've already found that being part of that group gives you access to knowledge from other groups where they say, hey, you know, have you noticed this is happening in my model? And so we can check to see how we're doing in that case, things like that. So just 2 days ago, the input data was made available for these simulations, and the runs look like they're probably going to be due at the end of 2020. So, and there's a couple of issues we need to fix before we can actually start those runs. And so the first of those is what we call the T-lay bug, because there's a problem in the layer temperature that the original error message that we got included the word T-lay. And so the basic problem is that we're having brief periods where the surface temperature is less than -200 Celsius. And this lasts for maybe 3 or 4 hours and then goes away. I'm showing an example here at NE256 that we're using to kind of poke at the problem, where you can see this blip of cold air is showing up. This is, I don't know if you can see the lines all that well, but this is the west coast of Greenland, and Baffin Island is on the other side here. So we have wind barbs. You can see that seems like it's something that's related to strange convergence of the wind. The problem gets worse at higher resolution. It basically doesn't exist at NE120. We start to see it at NE256, and it is much more frequent at NE1024. So we think it's related to the Dicor and perhaps the way that it's coupled to the physics. And so we have a basically like a critical path team that's meeting weekly and really kind of trying to push on this issue. Another problem we're having is that we're currently not bit for bit on restarts, and this seems to be connected to something happening in threading in P3. So, and then of course we haven't done any tuning at all for performance or skill. So I think we probably will want to tune the global cloudiness, for example. So, so those are things we're working on. I think that needing to have something done by the end of the year, we're well on track for that. Another thing we've been working relatively hard on, or at least starting to, is that we can't afford to do climate simulations, at least not frequently at all. And so how do we tune? And I really like what Wu Yin did with the high resolution version of E3SM-V1 in terms of using these short forecast simulations. He found that the change in model results due to changing a parameter in these forecast runs ended up being, in general, very good predictors of what you see in a climate change simulation. So this graphic is kind of illustrating that. It's a little bit too detailed for me to go into, but we're really investing in that approach. And so there are 3 ways to generate the initial conditions for doing forecasts. I'm listing them here. And so the SCREEN project, our team is currently intercomparing these 3 methods and trying to figure out which one is best for SCREEN. And we're also encouraging the creators of these 3 methods to merge their methods together and to try to come up with what is the best thing for E3SM to use and support kind of going forward. So, okay, and so the exciting thing here is that we can actually start to do science with the V0 version of the model. It might not be finalized, but just the only way we're going to find bugs is by poking at it. And so Hassan Beydoun has been doing radiative convective equilibrium simulations. We're showing a movie here of just the basically the domain of the model and the amount of precipitable water. And so you can see the evolution over time is that our model is aggregating into one big convecting lump. So this is typical of other models. It looks pretty reasonable. We're able to, in this setting, look at response to prescribed SST increase. And so our model is doing some things that are pretty reasonable. It's obeying the fixed anvil temperature hypothesis that is, I think, basically proven fact. It also more controversially and interestingly seems to be obeying Dick Linds's iris hypothesis in the sense that anvil clouds are retracting as the planet warms. And so, you know, I guess punchline here, we're able to start doing science. This is really exciting, and our model is getting interesting results. So, moving on to talk about the V1 model. So the critical thing here, the most interesting thing perhaps, is we're rewriting it from scratch in C++. I talked about that a little bit before. So the only thing I want to say here is that I'm showing a chunk of code in its original Fortran 90 and then the version after porting C++ Cocos. And so the reason why that we're doing this and the reason why it's going to be faster is it unlocks more parallelism on more machines. And so the result of that is a slight increase in complexity. And so without going into the details of the code, you can see that the original code is less lines than the new code. And I think that's going to be basically kind of standard with what we're seeing. I think a lot of people have angst over whether the code is going to be readable and intelligible by non-computer scientists. And I really feel strongly at this point, having tinkered with the code and actually ported some myself, that it is going to be legible. It's just not really going to be a big deal for most people. So probably the thing I'm most excited about in this whole talk is what's happening with the Dicor. So we've finished porting the C++ Dicor, we've finished porting the new non-hydrostatic version of the Dicor to C++, and in the next couple of weeks, we're going to submit a paper, the Gordon Bell competition, about that. And so this graphic on the right-hand side is showing preliminary timings for that as a function of number of nodes we're using on Summit. Keep in mind that the right-hand side, 4,096, is the total number of nodes on Summit. So using the whole machine, it looks like we can get to something like 0.8 simulated years per day or something like that. And so that is much better than 1 simulated day per day. So that's exciting. It means we might start to be able to do climate kinds of simulations. It's important to note here that this is a Dicor only timing test, and so adding physics will slow things down, but it's also not using the semi-Lagrangian infection, which we know is going to speed up. So the basic punchline is that order of magnitude, we're starting to be able to get simulated years instead of simulated days. So in terms of the physics status, we're wrapping up the P3 porting effort. It's not quite done yet. Instead of just having the people that are really experts at doing the porting do the porting, we've instead tried to slow down the conversion and have people that haven't done this kind of conversion before actually take functions and port them themselves. And so we have, I think, 6 people have been porting things that hadn't been before in this way. And I think that this is one of the metrics of the project that I'm most proud of, is increasing capacity in that way. So we're still, we are just starting to do the shock port now. And we think that's probably going to go a lot faster because there's just less code involved, and also because we have a lot more people that are spun up now. We're still going to use the Fortran version of RTMGP, at least until the ECP project provides us with a C++ Cocos version, but we do need to create the interface to our new coupler, and so we're basically beginning prep work on that. And it's becoming clear that now is the time where we really need to make more effort on the prescribed aerosol because it's connected to the radiation. And to be honest, this is something that I've been neglecting of all of the tasks on this project more than I should. So in terms of the coupling status, we are getting pretty far along. We actually have a completely new coupler where we're able to have processes talk to each other, and it is nominally connected into Seam as well, although the whole thing isn't working for full processes yet. And so the basic idea here with what we're doing is that each atmospheric process, whether that's Dicor or whether that is microphysics, is an instance of that atmospheric process class. And so having all of the processes behave in the same way makes it very easy to reorder the order in which you're calling things, call things in parallel, add new processes, remove processes, things like that. Also allows us to create a set of tools that all of the different processes can use, like the ability to regrid from one from one grid to another. And so that's the top level. Within within a particular process, we are breaking things down into an interface layer, which is where you essentially get all of the variables you need to use in that parameterization. And you do that through what we're calling the field manager, which you can think of as a souped up, modernized C++ version of pbuff. All of the variables instead of just some of the variables are communicated through this field manager now, and so that should simplify things. Another key bit is that by having the field manager only talk to the interface layer, that means that the actual process representation can be very model agnostic, or in other words, it can not use a lot of really kind of complicated model specific functions, which allows it to be used by other modeling centers if they want, but it also allows us to run standalone simulations quite easily for testing, and it allows us to create unit tests. So in terms of testing, our real goal is property tests in the sense of checks that the code's actually behaving physically, but we're actually doing a ton of regression testing now as well, which is what E3SM typically does, of just, am I bit for bit or not? And so something I'll point out is that at the bottom here, I say that finding the time in order to write property tests has been really hard for us because we have so many tasks that we need to do that are more concrete, that it's really important. We're trying to find time, but we're still struggling a bit on that. So a great example of a property test is vertical convergence in the shock parameterization. And so that's being shown on this graphic on the right-hand side. And so when we first tried this, you could see that at the surface, there's something very wrong going on, or there's a lot of resolution sensitivity, and we're able to fix that. And now we have good vertically converging solution. And when we looked into it, we found that the original formulation that we were inheriting in shock for two different aspects of the model were actually just kind of fundamentally inconsistent or wrong. And so this testing is allowing us to come up with better parameterizations. And it's really critical that we have separated out the interface layers from the actual parameterizations in order to be able to make this easy to do these sorts of testings. So, and that leaves me with my summary that I'll just let you read while I take questions.